fourth power, so not square.
You do not. There is no definition of that.
No. So just
You never give it. You haven't given the definition.
no, not yet. Yeah. So in this case, it's very well defined. You know the sine function. So, but now, in this case, I just said that you just take a inverse function. But first of all, it's not clear whether it is well defined first of all. Okay. And then next, what kind of function you get? You don't know that this function. And really, that what Abel did is to study very carefully about these functions. And very surprising thing is usually sine and cosine function is a real function. Yeah. Of course, in the complex function theory, you can extend to the function in complex domain, but at the beginning, it's just a real function. But to develop this theory, it's better to consider to extend the theory to the already complex. But how? So that's not easy. And before the Abel really tried to understand this inverse function, Gauss already did it. And Gauss found that certain reason that why we really need to consider that the complex functions, even though these are everything is real. And the reason is he was interested in looking at the relation, this kind of thing, not only two but any positive relation. And there exists some relation, much more complicated relation here. And he really wanted to solve this equation. And then he found that there exists always, if we n square roots. Actually, it appears that here it appears that the solvable equations in general. And then Gauss found that there is n square roots, and many of them are real in complex, not real value. So at the beginning, Gauss really puzzled like that, but then he found that if you think this function as a function in complex variables, then you can explain that why you get such n square roots. And this is a Gauss, but he never published his result, so nobody knows as a result. So when the Abel started his theory, the situation is it's completely nothing. So Abel started he only knows that this addition theorem, and using this addition theorem to find out the property of these functions. Okay. But this is, in a sense, very special, because 1 minus t to 4. And before Abel, the French mathematician Legendre he really studied such kind of integrals where degree of px is 4. Or maybe it's better to write always t, because x is using a different way. And he really studied carefully about this integral. And finally, he can classify the most basic integral of that form, such form. And his result is the basic one is this is one integral, and result calls this is elliptic integral. Of the first kind. And also, he found that, which is not so important, but that's a disputing integral of the second kind. And also, this is a integral of the third kind. This Today, these three integrals has sort of a kind of geometric meaning. Nothing that I will talk about later. But this is purely calculation, but somehow the result leads to this classification. And other integral is using this combination of these things, you get it. A combination of this integral plus some elementary function, you can always find this integral. In that sense, these three are most basic elliptic integrals. And other kind of such elliptic integrals can be obtained from this one plus elementary function. So that's a final result of the result. And now, Abel to do directly, but he tried to understand the, I prefer to use Abel notation. It's rather strange, but sorry. Maybe it's helpful to read the Abel's papers. Each mathematician uses different notation, especially in old times, so sometimes it's quite confusing to read. So what he studied is this one. He changed slightly the sign, first of all. And he assumed C is positive and E is positive. Yeah, because here everything is minus, so it's slightly different. But this is the reason that he chose this expression because he wants to extend the function to the complex analytic way.
Why C and E should be positive? Because you use C square and E square.
That's assume. Later, because that C and E is important later. So just assume. And then Abel considered x as a function of alpha. But he's of course very careful to define because in general it's not easy to define that this alpha, this function. So you have to start very slowly to define this function. Okay. So first, what Abel did is, let's start. First part is what is where is under this condition? I think it's so. What is the zero of this denominator? So T is 1 over C plus minus, isn't it? So just consider and define this number. This is sub number. And others define this is equals 1 is, I think, pi over 2. So just he indicates that yeah, it's this omega is something like similar to pi. So he uses, I think, seems use this notation. And now, then if x goes to from 0 to 1 over c, so this integral is decreasing or increasing. If you take a derivative, it's a positive, so this is monotone. Increasing functions.
Increasing,
Yeah, increasing functions.
X0 is 0.
Yeah, this is increasing monotone increasing. Therefore, and also point is x equals 0, then alpha equals 0. So just assume define that f0 phi is 0, then between x to you can define the inverse function x as a function of phi alpha in here. That's okay? Because it's a monotone increasing, so that you can take an inverse function of this. So I will be very careful about it. So you can only define this function at the moment here. And then I will get rather interesting things. So next, let's change the variable. So I mean, let's change the variable t to ti. Say this is s. Then what happens? No. S is not good. Just changes. Okay? So maybe it's better to say t is is over. And then, so here we write xi, and here I times ds, and then here 1 plus c s square, and here it comes e s square. So now, maybe, no, sorry, not xi, because s of this x. So I times 0 times x. We have this. So this is a purely imaginary number you get. And again, if x is 0 to now 1 over e, this integral this is again the monotone increasing. What do you say in Chinese? We say that this is
那叫递增，
the same?
递增。
No, maybe not.
You
can guess that.
单叫递增，递是 deliver something.
Uh-huh. So that we have used a different terminology.
这个是递吗？
Oh, I see. Oh, I see. That's more precise. Okay. So that's again that you